Okay, the section point 5.2 through 5.4 is about the statics, singularity, and the manipulability in detail. Okay, let's get started with the topic of statics. As mentioned before, the principle of conservation of the power is given by power at the joint as a sum of power to move the robot plus power at the end effector. If you assume that this robot system is at the steady equilibrium, it means there is no movement. At the time, the power at the joint will be equal to power at the end effector. So this is the base frame denoted by the S. It has two rings and the effector. Let's attach the body frame here. If you apply the external wrench denoted by the body frame, if you know the body twist, and then tau 1 and the tau 2 and the theta 1 dot and the theta 2 dot here, at the time the tau 1 theta 1 dot plus tau 2 theta 2 dot will be equal to FV transpose VB. Okay, it can be written using the matrix vector form. So we have this equation. You should memorize this equation can be obtained from the steady equilibrium, no movement of a robot. Okay, the body twist can be replaced with the Jacobian relationship in terms of theta dot, and both sides has the theta dot, so this part should be equal to each other. So we have this equation. Okay, joint torque at the steady equilibrium is obtained from the external wrench using the Jacobian transposition. On the other hand, we can get the similar expression in the space plane. In other words, this equation is independent of the coordinate. So without any subscription, we can subscript, we can write down this equation. Okay, if you have Jacobian transpose as a invertible matrix at the time, the J inverse transpose exists. So we can exchange each other using the Jacobian transpose or Jacobian inverse transpose. Okay. On the other hand, the robot is redundant and is larger than the 6. Robot cannot be immobilized. At that time, the internal motion appear using the null space projection of Jacobian. Okay. At that time, the steady equilibrium is not achieved in this case. On the other hand, if the n is smaller than 6, in this case, we cannot make the internal motion as well as, in other words, it can be the structure without any movement. It means no matter what tau we choose, the robot cannot actively generate force in the 6 minus n wrench direction. This direction can be find out using this equation. Okay, any wrench is here. The result is obtained as 0. At that time, this wrench exists in the null space of the J transpose. Is it right? Because this relation is satisfied, at that time, this wrench equation, wrench terms, will not make any will not make any torque in the joint torque directions because no actuators act in this direction. Okay. Okay, the singularity is very important issue. Okay, you know this. You know, we have talked about already the kinematic Jacobian in the previous lectures. The kinematic Jacobian is called as just singularity. Actually, there are many singularities, such as the algorithmic singularity, and the representation singularity. There are many, but we will talk about the just kinematic singularity in this section. Okay, let's assume that this is the base. The first joint, second joint is here, and the effector is here. Okay, let's assume that this is zero position. In this case, Jacobian will be the line segment in this direction. Is it right? But Jacobian inverse transpose will be the line segment like this. So this Jacobian let us know that this movement is not possible. On the other hand, Jacobian inverse transpose let us know there is no force application in this direction. Okay, so this loss of mobility, we lose this direction movement at the singularity, accompanied by adding of ability to resist arbitrary wrench in the direction corresponding to the lost mobility. It means, in this case, we can resist very big wrench applied to the end effector. Okay, so both has the trade-off relationship between them. Okay, as mentioned before, the mathematical definition of the kinematic singularity is independent of the choice, body or space Jacobian. The space Jacobian is singular at the time, body Jacobian singular as well, all the time. One more, the kinematic singularity is also independent of the choice of fixed and body frame. Okay, let's assume that the robot exists here. Let's move to here, maintaining the same posture. So t is the same each other, but the t prime should be obtained by multiplying the p in front side of the t matrix like this. Okay, let's obtain the twist of this relocated robot t prime inverse t prime dot. The t prime is obtained p times t, so inverse is obtained like this, and that p dot. Okay, so p's cancel out each other, so we arrive at the twist of the previous manipulator. So relocation of robot does not affect any singularity. The previous posture has some singularity. The singularity is maintained. Relocation of robot. Okay. Because singularity of the original and the relocated robot arms are same each other. Okay, so singularity is the intrinsic property. So any posture has singularity. The robot move anywhere, the singularity is maintained. Okay. this is the end frame, the body frame. Okay, let's attach another one. So body frame is moved here. So the T times Q will be used to denote the POE of this manipulator. Okay, let's obtain the twist T dot and the T inverse. Okay, Q appears like this, but the inverse relationship can be cancelled each other. So we arrive at the same result. It means if you have some singularity to T here, at the time if we add some joint to the latter part, it does not have any effect to the singularity. It has singularity. By adding on something, it's independent of each other. Okay, so the kinematic singularity are invariant with respect to the choice of the vector frame. So as mentioned before, the singularity is very intrinsic property. It is not bearing. Singularity is maintained all the posture. So singularity can be overcome by changing the mechanism structure. That's the only way to overcome it. Okay, we will talk about the 5 cases of singularity. The first one, the 2 collinear level joint axes will be the singular. Okay, the axis, the first one and the third one, but these 2 joint axes are aligned to each other. At that time, the WS1 and the WS2, maybe these directions are same each other, the same vectors, same one. And then let's attach the space frame or body frame, and then the Q vector will be the same each other. So this is all the same. So we have the same J1 and the J2. It means the column vector of the Jacobian and these the 2 column vectors are same each other. So the Jacobian matrix will lose the rank. The second case, the 3 coplanar and the parallel level joint axis. Okay, this 3 level joint exist on the same plane. Okay, so the axis will be the same. So we have the same omega 1 and omega S1 and omega S1. So this and this is the space frame. So Q1 will be the 0 vector. Q2 is obtained. Q3 is obtained. But the Q2 and the Q3 has the same direction with a different magnitude. So Q2 and the Q3 shows the same direction. So the J3 can be obtained by linear combination of J1 and the J2. Okay, it shows just some scalar multiplication example. By adding these 2 linear combination, we can achieve the J3. It means the first column vector times alpha 1 and the second column vector times beta 1. By adding a linear combination, we'll arrive at the third Jacobian column vector. It shows this matrix lose rank. This posture is a singular. Okay. Okay, third case is about the 4 level joint axes intersecting as a common point. Okay, there are many level joints here. Some case the 4 level joint axis, square axis intersecting at the one point, one common point. Okay? At the time, if we attach the coordinate frame here, maybe the q vector will be assigned as a 0 vector. Is it right? All the q can be assumed to be 0 because the intersection point can be chosen as a reference. So WS1, WS2, WS3, WS4 are different to each other, but the linear velocity will be the same because the q is to 0. So it has the three different elements. The fourth element, post-Jacobian, can be obtained by using the linear combination of the first one, second one, third one. So this matrix will lose rank. This configuration is corresponding to the singular one. Okay. Fourth case is about the pole planar level joint. Okay. In the same plane, level joint is here, level joint is here, level joint is here, here, but all the axes exist on the same plane. Okay, the WS1, WS2, WS3, WS4 will be described using these two elements. If we choose the 0G. On the other hand, if we attach the reference frame here, Q1 and the Q2 and the Q3 and the Q4 vector will be described using the X and the Y element without 0, without Z-axis, because all the joint exist on the same plane. Okay, in this case, the linear velocity is obtained the cross product of omega and the Q, so we have the last element only. Okay, let's collect J1, J2, J3, J4. It has every column vector has the three independent elements. So post-Jacobian column vector can be described using the first one, second one, and third one as a linear combination. Is right? So it loses the rank. So in this case, singular. Okay, last case is about a 6-level joint intersecting a common line. Okay, this axis like this, the second joint axis like this, third, fourth, the fifth and sixth. Let's assume that all the joint intersecting one common line. Intersecting one common line like this. Okay, in this case, if we attach the S frame or P frame, at that time the Q vector is obtained. Q1 and the Q2 and the Q3 and the Q4 and the Q5, Q6 will be described using just the G coordinate. Is it right? So omega is different each other, but the linear velocity in the the Q vector is described only one element. So omega cross Q will be described in the X and Y direction. All the time G will be 0. Okay, so J1, J2, J3, J4, J5, J6. In here, every column vector has the 5 independent elements, but we have the 6th column. So the last column can be expressed as a linear combination of the remaining 5. So it loses rank. So if the 6-level joint intersect at a common line, the robot structure is a singular. Okay. till now we have talked about the 5 cases of a singular configuration. It's not easy to discern the singular configuration. So many cases we cannot distinguish the singular posture from the normal case. Okay, so the manipulability concept suggested by the Jine Yoshikawa professor in Japan. Actually, he retired already, but he must be a genius. He make the many advance in robotics. Okay, one of the his idea is about manipulability. Okay, the kinematic singularity presents the binary decision. Is it right? Structure is the singular or not. It's not good concept because let's assume that this is the base. This is the first link. First joint has the one degree. Very small variation from the zero position, and one more. This is the 1 degree. Maybe it can be treated as the zero position because the variation is very small. Anyway, this is a non-singular, is it right? This is a singular. But the structure is very similar each other. This kind of a configuration looks like singular near the singular, is it right? Okay, so it's very reasonable to think about how close non-singular configuration is to be singular. In other words, we can even determine the direction in which the end effector ability to move is diminished, or to some what extent. Okay, the manipulability shows or suggests how close the posture to the singular configuration. How close? Okay, so the manipulability can be used as a measure to determine the how close is it to the singular configuration. Okay, for general n joint open chain, the task of space with the coordinate q. In this case, the manipulability ellipsoid can be obtained using the Jacobian relationship. Okay, let's assume that the unit circle contour is given, and then if we apply the Jacobian inverse relationship like this, at that time we have the inner matrix JJT inverse. Okay, for the notational convenience, let's assume that this is assigned as A. So we have the Q dot transpose A inverse Q dot as a 1. Okay, A is given, but Q dot is different. Okay. Now we will talk about the Q dot transpose A inverse Q dot as a 1. It exists in the m-dimensional space because the Q dot belongs to Rm. Okay. Okay. Let's obtain the eigenvalue and the eigenvector of the A. Eigenvector is denoted by the VA. Eigenvalue is denoted by the lambda I of the A matrix. Okay, here the A inverse is required to this equation. So using the eigenvalue and the eigenvector, we can describe the A inverse 1 over lambda and V transpose. It is called as outer expansion of matrix vector equation. Okay, it is corresponding to the A inverse. Okay, so if we expand this equation from the 1 to m, then the first term will be the 1 over lambda 1 and the q dot transpose v, and then I'm sorry, the v1 transpose q, and the same one will appear 2 times, right? It should be added from 1 to the m. All addition should be equal to 1. Okay, q dot is variable here. Okay, q dot is equal to v1 with the square root lambda 1. It is applied to the here. What happened? It is equal to 1. Every eigenvectors are orthogonal each other, so remaining terms will be the 0. So we have just this equation, but 2 times square root lambda 1 will be cancelled out to 1 over lambda 1, and the v1 transpose v1 will be 1, and this is also 1. So this term must be solution of this equation. Okay, so let's draw this term in the v1 direction with the magnitude of the root square root lambda 1, like this. v1 direction and the length of the square root lambda 1 here. On the other hand, q dot is achieved v2 square root lambda 2. Maybe the second term will appear, remaining terms will be cancelled out each other. So let's draw this one. The q dot is given by the v2 direction with the magnitude of the square root lambda 2 and the square root lambda. On the other hand, the v3 direction is achieved like this. Like this, we can draw the ellipsoid to denote the mobility. Maybe the v1 direction movement will be very easy. On the other hand, v3 direction movement is not easy compared to the v1. Like this, we can know that which direction is available to move end effector. On the other hand, the small size of length shows how difficult to move this direction. Okay, furthermore, the volume of the V, this volume of the ellipsoid, is proportional to the product of the semi-axis length. So semi-axis length will be the lambda 1 and the square root lambda 2 and the square root lambda n. So by multiplying all terms will proportional to the volume of this ellipsoid. So we have this equation. All the multiplication of the all eigenvalue will be equal to determinant value of the A matrix. So square root determinant JJT shows the volume of an ellipsoid. Okay. Okay. We should know how close is it to the singular configuration. So we will suggest 3 kinds of measure. The first measure is about ratio of longest and the shortest semi-axis length of a manipulability ellipsoid. The maximum eigenvalue will be the square root lambda 1. Minimum eigenvalue will be the square root lambda m. So if we make the ratio between both, we can estimate the shape of an ellipsoid. It looks like the line segment. It looks like unisphere. Those kind of things can be estimated by comparing the length of major and minor axis. Okay, it will be larger than 1 all the time because we, according to the definition of this one. Okay, so as the robot approaches the singularity, the mu1, this value, will go to infinity. At the time, we can know that if you have the big mu1 value, it's very close to the singular structure. So we should move to the unsingular, non-singular configuration. This value shows how close is it to the singular configuration. Okay, the second measure is the scale of the mu1. So the square root is removed by multiplying 2 times of the same value. Okay, fortunately it has the name. It is called as condition number of A matrix. Okay, condition number is defined maximum eigenvalue over minimum eigenvalue of A matrix. So it can be used removing the square root operation. Okay, the interpretation is the same. The smaller value will be preferred. Smaller value will be near to unit sphere. The larger value of the mu2 looks like the line segment or line segment. Okay, so the condition number of the matrix commonly used to characterize the sensitivity of a result of multiplying of the matrix of vector to small error in the vector. So this condition number is used to denote, to express how close it is to singular structure. Okay, third measure is about the volume. Okay, volume is obtained by the square root value of all the eigenvalue multiplication. Okay, it can be obtained determinant of A. In this case, the larger value is preferred. Larger value shows the big volume compared to the big volume shows the good manipulability in omnidirection. In any direction we can move. Okay, the larger value is preferred, will be better. Okay, in this case, you can use the first and second and third measure, but first measure and second measure is used to shows to have the small number compared to the third measure. Okay, in the case of third measure, the small or larger value is preferred. Well, larger value will shows the good manipulability. Okay, compared to the manipulability ellipsoid, the false ellipsoid is obtained as orthogonal map. Okay, maybe we know the unit torque contour will be used to denote the false ellipsoid. Okay, so this is the tau transpose, this is the tau. Okay, so the unit tau contour is used to describe the false ellipsoid. Okay, so this inner part, this one, okay, we need to obtain the inverse relation, so this is assigned as a B inverse vector, so B is equal to the inverse matrix of the A. So both are orthogonal each other. For the false ellipsoid, matrix B plays the same role as the A in the matrix manipulability ellipsoid. Okay. On the other hand, since the eigenvector of any invertible matrix A also eigenvectors of the B, the A and A inverse has the same eigenvector, but the eigenvalue is different. A has the eigenvalue as lambda, A inverse has 1 over lambda. Okay, like this, the eigenvalues are different each other. Actually, both are reciprocal each other, but eigenvector is same. Eigenvectors are same each other. Okay, how about the volume? The volume of manipulability is obtained by multiplying all the eigenvalue, and then we take the square root operation. On the other hand, the VB will be proportional to the inverse value of this one. Okay, 1 over square root lambda 1 through lambda m. Okay, but the VA times VB will be the same, will be the constant all the time, independent of the joint variable theta. Okay. So positioning the robot to increase the manipulability ellipsoid volume measure. At that time, it reduces the pulse ellipsoid volume measure because VA times VB is constant. Okay. Okay, so this explains the observation made at the start of the chapter. As the robot approaches to the singularity, VA goes to 0. On the other hand, VB goes to infinity. Okay, like this, both are reciprocal, both have reciprocal property in viewpoint of eigenvalue. Okay. I was so exhausted from many items to do, work to do. Okay, anyway, I finished the chapter 5. So you should solve and submit exercise 1, 2, 7, 10, 11, 16, 18, 13. I'm sorry. Is it right? 13? 13? 13, 18, 19. Okay, let's remove. Okay, 18 and then 21. I reduced the number of the homework. Okay. Okay, the due date is the May 3rd. Okay, you should upload or email me, including the attached file. Or more, if you let me know what numbers you cannot solve until end of the April, I will include the solving procedure in the next lecture. Okay. Okay, maybe next week I will talk about chapter 6, and then we should have the real-time online class to show us how to solve chapter 5 or chapter 6 exercise at the time. Anyway, if you have any questions or some comment on the exercise number,